So Camille, that's a pleasure to have you here. And so that's I don't introduce you, but light is really shall we have because I am not visual enough. Yes, there is to make this good. Yeah, on the left. Yes. No. I don't know if I can complete it. Yes. It's the other one which can close this. Yes. No. This is it. So we will do it just but this one, the problem is this one is okay. Sorry. Okay, that's good. Okay, so I'm sorry, you can go on. I just have to do something. Sorry. Je voudrais me mettre en
Ouais, je sais, ouais. Tu veux...
en côte, voilà.
Ah oui,
C'est bon. Voilà, comme ça, je peux faire les choses sans te déranger.
Okay.
Je sais pas, tu peux le faire là? Je sais plus comment.
Ça dépend.
So thank you, Camille, for coming.
Hello, everyone. Thank you for being here, and thank you, Paul, for organizing this conference and for the invitation. So I am Camille Coron. I am working in the Laboratoire de Mathématiques d'Orsay in Université Paris-Saclay. And today I will present you work that I did several years ago together with. Comment on fait ça? Okay. Together with Clément Calange, who is a biostatistician working in the Office national de la chasse et de la faune sauvage, Christophe Giraud, who is a statistician working in my lab, and Romain Julliard, who is a conservation biologist. Our aim in this work is to be able to produce some relative abundance maps for several species of interest. I will explain later on what I mean by that. And in the end, I will show you some more recent developments that we did, that I did with other colleagues on a different subject, but whose mathematical problem is related. So the general context of our problem is the following. So we have two data sets that come from different protocols. The first one, we have a very precise protocol, and the second one is a very imprecise or unknown protocol. And obviously, the first data set is very expensive and a small one. And the second one is a big data set that is very cheap. And our aim is to benefit from both data sets and to combine them to have better estimations than what we had using only the standardized data sets, the first data set with a precise protocol. More precisely, I can describe the data that we will use in the end. So we consider birds observations in Aquitaine. Aquitaine is a region in the southwest of France here. So these are birds observations. So the first data set that we have is called standardized data set, which means that observers had to follow a very precise protocol to participate to this data set. So what is the protocol? So the space Aquitaine is divided in 63 regions, and in each region 10 points were fixed and chosen, and a given observer had to go to each of these points, observe for 5 minutes and report the species of every bird that he or she observed or heard. And there were only 12 species of interest for this data set. It's a professional data set. The second data set is called an opportunistic data set, which means that we do not impose anything to observers, basically. More precisely, it's just a website on which anyone can register and report the observations that they make on birds. And they are not forced to stay for a given amount of time, and they are not forced to report all their observations. So you can do everything, anything you want. And here you see that we have a lot of observations, but there is no the spatial repartition of these observations is not uniform, and we don't know the amount of time spent in each region of space. But we have a lot of data. And also there are 34 species. These are mainly common bird species. And the last data set is like the first one, the standardized data set, but with fewer points, but the same species than for the opportunistic data set. We will use this one. So our aim is to combine these two data sets to make some estimations, and we will assess the properties of our estimations using the third one. So our aim here is to make some species relative abundance maps. So what does it mean? It means if you have space like this, divided in several regions, then you want to be able to compare the number of individuals for a given species. You want to compare the number of individuals in this region and in this one. And the second question of interest is what is the interest of opportunistic data? Here, you see that if you have only opportunistic data, you cannot say anything because you do not know whether, let's say you have twice as much observations of a given species here than there. You don't know if it's because there are twice as much birds here than there, or if just people spend twice as much time to observe here than there. So with only opportunistic data, you cannot say anything. If you use only the standardized data set, you can do something. So the interest is, what is the question is, what is the interest of opportunistic data set here? So to answer these two questions, we consider, we are going to model the data sets, the data that we have. So space is divided in several regions, as you might read here. They are indexed by J, and species are indexed by I, and we denote by Nij the number of individuals of species I in region G. And so our aim is to estimate Nij divided by Ni1 for all j. To this aim, we have two data sets, a standardized data set that is indexed by k is equal to 0, and the opportunistic data set indexed by k equals 1. And our modeling of the first assumption is that the number of observations of species I in region J for the dataset K, it follows a Poisson distribution whose parameter is the number of individuals of species I in region J, which is merely what we want to estimate, times an observation, a kind of observation intensity that, for instance, for the moment, I divided by 4 ij. Here, the Poisson assumption is a very classical. The general idea is to say that at each moment you have the same probability to report, to make an observation and to report this observation of a given bird, of each bird. Also, we can add some noise here. It works also. Now, our main assumption here is that we decompose the observation process in a product of two quantities. The first one that depends only on the species and the data set, and the second one that depends only on the region and on the data set. Here, this PIK term will typically take into account the detection probability or reporting probability of a given species for the dataset K. For instance, you know that for the opportunistic datasets, people are not forced to report their observations. So maybe, depending on the species, they will report their observations or not, because they like the species or because the species is rare or something like that. And this second term will typically take into account the total amount of time spent on the field on the region J for the dataset K. So our modeling assumption is that the impact of the species and of the region are independent on a given dataset. We are forced to make some hypothesis, otherwise Nij will not be identifiable, obviously. Here, you see that, so this is our model. You see that Nij like this is not identifiable again, because if you multiply all Nij and even Nij divided by Ni1, because if you multiply Nij by some lambda j, for instance, and divide Ejk by the same lambda j, then your data will have the same law, but the Nij will not be the same. Here, what is the solution is that we have a standardized data set that does not allow to divide Ejk as we wish. So here, our assumption is that due to standardized data, for the non-standardized data set, we can compare the effort made in two different regions. So you have that Ej0 divided by E10 is known for all j. So we have some constraints that ensure, and we can prove that using an appropriate change of variables. We can prove that the relative abundances Nij divided by Ni1, this is what we want to estimate, or differentiable. So here, the expectation of xijk is equal to the product of these three terms. And if you take the logarithm of this, you will have that you have a generalized linear model for which we can consider the maximum likelihood estimator for the relative abundances Nij divided by Ni1. And note that you can also do this by considering only the standardized data set. So I can also define a maximum likelihood estimator of the relative abundances when using only the standardized data set. And our aim will be to compare both estimators. So our theoretical result is the following. The first one is that the expectation of our estimator by combining both data sets, when the effort in the opportunistic data set goes to infinity, which is exactly what we expect from this type of data set, because we have a lot of observers, or maybe more, a lot of time spent on the field, then this converges towards what we are interested in, which is here it's the relative abundance. And the second point of our result is that the variance of this estimator, when the effort again goes to infinity, converges toward the variance of the estimator when you use only the standardized data set times a parameter, a quantity that is lower than 1. So this result states that when you combine both data sets, assuming that the opportunistic data set has comes from a very large effort of effort on the field, then the combining both data sets improves our estimations. It's particularly interesting when the species I is rare, which means that here this is very small. Also, when the species I is hardly detected in the opportunistic data set, which standardized data set, sorry, which means that Pi0 is very small, and also when you consider a large number of species, which means that this term would be very large. And the last comment on this is that the estimation of the is also defined even if species I is not observed in the standardized data set, which obviously you cannot do if you have only the standardized data set. So combining the two data sets allows to make some predictions also for species that were not in the standardized data set, which is particularly interesting. For real data now, so here I will assess let's say an illustration of the theorem, but using real data. For the moment, let us focus only on the two first lines here. So here I give the median of the Pearson correlation coefficients between the estimated and reference relative abundances. What do I mean by the reference relative abundances? These are the estimations that we do using that we can make using the third data set. So here, these numbers are between -1 and 1, and the higher they are, the better our estimate. So here, this is when we use only the standardized data sets. And here, when we combine both data sets, so you see that we improve a lot our estimations by combining the two data sets. And also, we can make some predictions for the species that are not in the standardized data sets, which is obviously not possible when you have only the standardized data set. And also, these predictions are better than the one that you do only with the standardized data sets for species that are in the standardized data set. So this is the illustration of our theorem. In fact, what happens for our special data sets that we have is that the standardized data set that we considered was a very good one, which means that it was a large standardized data set, which is not really what you expect from a standardized data set. You expect that the problem with this kind of data set is that they are expensive and so they are small. But here this one was large, so we wanted to see whether our improvement due to the combination of both data sets was maybe more interesting if we had a smaller standardized data set. So here we artificially reduced the standardized data set that we had by taking 1/10 of the observations, so only 1 point per region. Here you see that the prediction capacities of the standardized data set is catastrophic. And by combining both data sets, so the reduced standardized data set and the opportunistic one, we have a very good estimation. How much time do I have? Here, at this point, at this stage of the work, we could already make some abundance map, relative abundance maps, but the biologists we were working with told us that the problem is that it was not very realistic to neglect some habitat structure of space, because you know that space will be covered by several types of habitats. let's say some forest or some agricultural regions. And these habitats will have an impact both on the position of observers and of observed individuals. And as we do not know the habitats in which each observation is made, then this should or could induce some bias in our observations. So we wanted first to introduce some hidden variable to model this habitat and preference of individuals and observers for these different types of habitats. So here we assume now that each region is covered by some habitat age, and we assume to know this coverage. Here, for the real data that we consider the ground occupation. I will show you next. And we assume that the density of a species I in the region J is proportional to some preference parameter, SIH, which measures or quantifies the preference of a species I for the habitat H. Also, for observers now, we have, I recall that we have two data sets, and we assume that we know, so here we cut space using smaller cells, here, like a city, for instance, in which we know that the observation was, but we don't know in which habitat occurred the observation, but we know again the coverage of this small cell in habitats. And again, at the scale of the cell, we assume that the density of observers is proportional to some preference, habitat preference of observers. In the end, you have that the number of observations of the species I in the cell C, so this is a smaller scale for the dataset K, follows the Poisson distribution, whose parameter is the abundance of species I in the region J, region J in which lies the cell C, times the effort made in the cell C for the dataset K, times the let's say the detection probability of species I for the dataset K, times a term that takes into account the probability of presence of individuals and of observers in all the different possible habitats. Here, you don't have the linear model as generalized linear model as previously, but we can make our observations using a Bayesian framework that we implemented using JAGS. So we take some uninformative priors, and then knowing the data set, we give the a posteriori distribution of parameters. Here we test our estimation by using simulated data. So I fix the number of species like in my real data set, and then I fix all the parameters, and then my aim is to recover them using, and I'll simulate some data sets, and I want to recover the parameters, real parameters, using the real simulated data set. So here I give the examples for the relative abundance. Here, in red, these are the real values. In blue is the a posteriori distribution using both data sets. In black is the a posteriori distribution of the relative abundance using only the standardized data sets. So you also see the reduced variance when combining both data sets, as we had previously. And finally, in the dotted black lines, these are the posterior distribution of the relative abundances when we neglect the habitat structure, whereas the data were simulated assuming habitat structure. So obviously, it's not a good result. Maybe I will stop here for that. Using real data we can make, as previously, some assessment of the performance of our estimations. Here, this is when we combine both data sets and consider habitat structure. Here, when you consider only the standardized data sets with habitat structure. And finally, when we combine both data sets, yes, but without habitat structure. Here, so you see the improvement was here for the second work. It's not that much. In fact, this is due to the fact that for the data set that we have, we expect that a lot of species are generalists, in fact. So there are maybe a lot of them are not very impacted by habitat. However, you see that so a byproduct of our work is that we can give the preferences of each species for each habitat. Here I give the mean preferences so over all species for the different types of habitats. Here, for instance, is the urbanized area. So you see that this is not the place that is preferred by birds. And here, these are forests. It's better habitat for birds. And we can do this species by species. And finally, we have some, we can make some relative abundance maps, and you see that these maps are different whether we include the habitat structure or not. This is for a special species. I can have some minutes to talk about recent work in a completely different field, but with the same program of dataset combination. So here, this is the work in progress with Jean-Michel Poggi and Benjamin Oder, who are in my lab. So the context is completely different. We want to focus on air quality monitoring. So our aim is to establish some concentration maps in some particles. So NO2 and particulate matter. So this is an example of concentration map in a city of France. So to make these concentration maps, we have the output of a deterministic physico-chemical model, and then we have two sets of measurements made by two different types of devices. The first one are fixed stations that are quite, I think, quite big, but also very precise. They give precise measure, but they are very expensive. And another type of data set that we have are microsensors that give imprecise measures but are very cheap, so we can have several of them. The idea is that for the city that we considered, here we have 5 stations, and we could have, let's say, 100 microsensors. And in the end, we could also have a third data set of microsensors that could be put on cars, for instance. So they would move all over space, which is, again, another problem. So our aim is, again, to combine two sorts of data sets. Here, the problem is not exactly the same as for birds. For birds, we do not know the protocol. Here, the protocol is known, but the problem is that the quality of measurement is not good for the second data set. But this is, I think we could do we can do the same, but some modeling. We started this work, but I can just to give some ideas. So our idea is to start with the physico-chemical model output, to model, so to assume that our aim is to correct this model. So we want to model the bias or the error made by this model, and to estimate this bias using the measures of fixed stations and also of the microsensors. And the questions are maybe the same or closely related to the one that we had for the birds. So how microsensors can help make our estimations, whereas we don't really know their properties. How many microsensors is the best for us, knowing that there are cheap but maybe they do not. If you have very few big sensors, probably it's not very interesting to have some of them. And also what is the best distribution, spatial distribution of stations and of microsensors, for instance. And these are the references for the first works. Thank you very much.
Other questions?
Yes.
I have some. I'm working with fishery scientists, and we are facing the same kind of data because we have two kinds of data: the survey data, which are quite the same as you have, and we have also some mandatory data that's the commercial declaration from the fishermen, except that they are declared at core level. That is that there is some administrative limits, and the fishermen have to report all the catch fished in the same large administrative limits. And so we try to combine them. And of course, there is some additional issues. The fact that the fishermen have like some preference for sampling process. And so we are trying to combine all that. Do you think that your approach could be adapted in this situation? Because we are doing some, so there is some parts which are quite similar. But,
so the fishermen do not tell you where they went to fish.
Actually, we have some items of fishing points because we are following the fishermen by some GPS.
Yes.
So, and we are able to identify the portion of the trajectory where they are slowing, and it's most probably the point that they are fishing.
Okay.
So we have some good idea on where they are fishing, but we have also this aggregation of the data.
Okay.
So we don't have precise location.
Okay.
Precise catch associated with the location. So the fact is that if we are
the pooled, the observations are pooled together.
So it's
we could do a model like this one, exactly. Maybe that would be the best, but I'm not sure if the approach can be similar, but I don't know if the results will be exactly the same kind of.
Maybe we can discuss that.
Yeah, great.
Thank you.
Hi, thank you very much for the talk. Very interesting to know that citizen science project can actually make a difference. That's great. And I was wondering if you made any assumptions regarding the distribution of abundance, the probability distribution.
No, we do not make any assumption regarding this. That would be interesting to make some continuity assumption, maybe to say that when two regions are close, maybe the two quantities are correlated, but this was not our approach and our question. Our work is at very large scale, so larger spatial scales compared to the living area of birds. So this is what is behind the fact that we consider that these are independent.
What about for the prior, for your Bayesian analysis? You assume something about the distribution to be a beta distribution, for example, or something like that?
So for the Bayesian part, we took some gamma distributions, but very flat for the prior. So.
Yeah, I'm asking because in ecology, this day is a huge deal. What is the distribution of abundance at a regional scale? And people is fighting between, the unified theory about where we say that it's whatever a Fisher-like or a Knox-Lewis-like or a normal-like or a beta-like. So that's what I was wondering. Okay.
No, we do not. No, we make our gamma assumption because we want this to be positive. No, it's not. No, I'm not an expert on that. And well, in my field, I would tend to suggest to make a modeling assumption that would derive some probabilistic form. But this is what I do. But I don't know.
Yeah, it would be nice to know if you can say something about what would be the distribution.
Yeah.
That kind of
Yeah, no, that was not our approach at all. It's just the mean that we were interested in.
Like,
I don't want to delay the schedules. Like, it's quite.
So I will just stop to record one moment. Wait. How is it story? Okay. So Marie-Pierre, thank you to give the second talk.
So thanks a lot for the invitation. For the one who are attending to the seminar in EcoDep, the previous version, so it's quite similar. I was hoping to present the work on the fisheries data, but it was not ready, so I switched to this one. It's about movement ecology and some work with some colleague about how to analyze the movement, the habitat preference for animals by following their movement. So the movement ecologists are very inspired by a paper from Nathan and co-author in 2008. In this paper, the author described that the fact that the movement of an animal depends on several aspects of its personality. And one is external and environmental factor, which has impact on his movement, but also some internal states, and of course, his motion capacity and his navigation capacity. All this together and all this combined gives as a result, we have the movement of the animals. And the idea is that by studying the movement of the animal, you can inform, you can have information on the internal state of the individual or how they react to their environment. And by internal state, people most of the time think, so ecologists most of the time, they think about that easy feeding or traveling or transiting to another area. So that's the main idea of movement ecology is that by studying the movement of individuals, you can have information on how they react to the environment. And if you have data of several individuals, you can also maybe study the interaction between individuals. So in this presentation, I will focus on habitat preferences and how you can infer habitat preferences from movement data. But before that, I will just briefly present what movement data are and how they are considered in ecology in general. So it's basically a time series of position, which might or might not be sampled at regular time. So here's an example with different sampling with irregular sampling process. And of course, you don't have the information on the actual movement, you just have the position over time. And you also have, you can have unprecise localization of the position. So instead of having the actual position, you have some noisy version of this position. And you are interested by studying this kind of data. So from a statistical point of view, it's just a time series of bidimensional data associated with the time. And people tend to, the question that people try to address is that in behavioral ecology, is that can we, how are we able to identify some different states, some different portion in the trajectory? And it's basically doing some segmentation on the movement path and associated to this kind of movement, some states, which then will be studied by the ecologists and trying to make information on how it's linked to the individual itself. So here it's Peruvian booby trajectory data. So here is a colony of birds and they are traveling to some area where they are feeding actively and then coming back, and the segmentation process identifying the travel to go on the fishing zone and the travel to go back to the main colony. And here you have two kinds of movements, and it mainly depends on the sinuosity of the trajectory.
because when they are fishing actively, they tend to have like very erratic movement, while when they move from one place to another one, they have a more direct trajectory. So that's one question that we want to address, is that are we able to identify some pattern in the movement, which will then be linked to the state of the individuals. And another question is the habitat preference. Here it's some sea lions data. And so we are following sea lions using some GPS data. And we are also having some information on different habitats. So here it's bathymetrics, that's the depth of the sea. Here it's a map of the slope of the bottom of the sea, the distance to some specific sites which are known to be very important for the sea lions, and the distance to the shelf, to the coast. These two ones are very similar. And we would like to understand if the trajectory or the repartition, the spatial distribution of the sea lions density is somehow linked to this habitat measurement. Most of this sort of data are analyzed using some discrete time model, and the first step is to describe the movements in a way that can be analyzed using some signal processing methods. And the basic representation of the movement is to describe the length of the step and to add the angle here. So we have a series with two variables observed at the same time, which is the succession of step length and turn angle, or you can also have some direction. And you analyze, they will be analyzed using some classical segmentation model. For example, classically, you can use, and that's the first one we are done, you can use a hidden Markov model and to have some very simple representation of the movement using the metrics I have described before. But there is also some change point detection approach using the initial work from Marc Lavielle, which has been extended by Émile Le Barbier and Franck Picard in the following. And basically, it's just the idea is just to consider. So here I just represent one signal, but you can have several signals at the same moment. And you just assume that there is some homogeneous pattern in the trajectory, and then it switched to another one. And so there is like many methods to do so by applying the idea proposed by Marc Lavielle. And you can also adding some constraints by saying that, okay, you have this segmentation process, but when you go back from here, you can see that these two segments are very similar, and you can want to cluster them together and to associate with the same state, internal state. So the method proposed by this author are very easy to be used and to be generalized to analyze several signals at the same moment. And so that has been done. But maybe the drawback of this approach is that they don't propose very satisfying movement model, because basically what they are assuming for the model is just like we are interested by a change in the mean here, and so you have some simple assumption about things that it's a Gaussian observation and they are independent or this kind of stuff. So we would like to propose first, we'd like to consider the movement not only as a time series, but it's a time series which is evolving in a spatial space. So we have to account for the spatial dimension also. And we also would like to present some more meaningful movement models. Again, we can discuss the advantage and the drawbacks of consider the movement as a continuous time model or using some discrete time model. One of the main concerns, to my opinion, is that if you stick to the discrete time model, is that you have to be sure that you have regular time step so that your model is realistic. And it could be more difficult to achieve to have a regular time step, even if your device is set up to have a regular position. Depending on the environment, if you are in a very deep forest, for example, it's very difficult to have a GPS signal. If you are under the sea, you can't have any GPS signal. So there is many of environmental conditions which goes against the fact that we have regular time step. So it's important to propose some model which can handle unregular time step, and the continuous time model is more flexible to do so. So I will not discuss further about this, the pro and the context. The fact is that the continuous model are a bit more difficult from a theoretical point of view. And so they have received less attention in the ecology community. So one is very useful because it's very easy and it's like a normal distribution, but the pure diffusion model, the Brownian motion. So you just assume that the movement of the animal follow a Brownian motion. And because I will extend it later, I present it in some kind of stochastic differential equation, but there is no stochastic differential equation here. It's just a Brownian motion. And if you do so, it's a very easy model. You know the transition probability, so you can have the likelihood, and the likelihood is very easy to optimize. So it's a very straightforward approach, except that there is no ecological meaning in this kind of model. And of course, no animal will follow a Brownian motion. So there have been some improvements. Here it's using a North-Steinman process. The idea behind this process is that when you consider animal, most of the animal we are considering are central place forager. So you can assume that this parameter mu is a central place where they are linked for, and they tend to be attracted by this point. So you can find some ecological meaning about that, but you don't consider the habitat and the fact that the habitat that the animals are visiting is not homogeneous. So it's also like kind of accounting process. What should I do? Can I say I admit it?
Yes, please.
Okay. So we would like to propose, these two models are very popular for one specific reason, is that transition between one point to another one is known and is explicit. So you can write the likelihood and you can optimize it very easily. That's why they have been so used in the community of ecologists. Oh. Okay. At the beginning of in 2000, Brillinger and Scouser proposed a new approach, saying that what we'd like to understand is that how the movement is linked to the environmental space, how they react to how animals react to their environment. And to do so, I will model the movements of individual here by saying it reacts to some potential on the environment, and this potential function is here called h, and the speed of the animal is linked to the gradient of this environment, and so it tends to go in the very attractive place and to avoid the place which are not suitable for him. And by doing so, you would like to estimate this deterministic part, which is the part you are interested in, and you account for the fact that you don't monitor completely the environment, and also that the animal is not a physical particle, and that he has his own ideas in his head that you will never know. So you add this random term here to account for this this discrepancy between the deterministic part. And by giving some deterministic form to the potential of the environment, you hope to estimate it. Of course, if you do so, you don't have anymore the explicit transition density between two successive positions, but you can use some discretization or some approximation, and that we have explored during Pierre Clohaget's PhD, and that's by giving a very, I would say, semi-parametric form from the attractivity of the environment. So we just use a mixture of Gaussian distribution, except that we don't force the mixture to sum to 1 because there is no reason to be a distribution probability. So we just to have some very flexible shape, and we can choose the number of components in the mixture, so that we have a very flexible way to represent the attractivity of the environment. So by doing so, we have compared different approximations to be able to estimate the parameter of this kind of model. And we have, so the classical one is the Euler approximation, but there is like second order approximation, the one given by Ozaki and the other one given by Kessler. And we also compare it with an exact approach based on a particle approach, which is a Monte Carlo Monte Carlo EM estimation of the likelihood based on exact simulation of the diffusion process. And so we compare all this approach to estimate this kind of model, and in the context of animal ecology, where we have like kind of sparse data compared to the, I would say, the financial application, where you have like, when you have high trading information, high frequency trading, sorry, you have a lot of information, have a very small amount of time. Here, I can see in movement ecology, we have like more sparse data, and so the Euler approximation is highly questionable. And the truth is, like in many applications, the Euler approximation provides some biased estimates of the true process. But Ozaki and Kessler approach, so the second order one, give really good results and very similar to the MCEM approach, except that they are more easy to compute, and even the code is more easy to apply and to develop. So that's doing so, we assume that the position is perfectly known, which is not the case. So we try to look at the situation where you have like only partially observed stochastic differential equation. That is, you have noisy observation of the position, and we have like and you still consider some stochastic differential equation which are observed using some Gaussian noise here. And if you look at this kind of, you can see that if you are using some EM algorithm, you should estimate this kind of quantity, and this kind of quantity just involve two successive positions. It's a sum over the whole trajectory of only two successive positions, thanks to the Markov property. And doing so, you have very clever algorithm proposed by Olson and Westerborn in 2010, which proposed to have to make the estimation of just with a one forward algorithm, and the backward pass you are supposed to do is made online at the same time of the forward pass. And it's it's a very nice and clever idea, and it's very efficient, except that you have to know the transition between two successive particles. And so again, Pierre and Sylvain Lecorf I've worked a lot on that, and we prove that it's also possible to do the same, to use the same idea, the same tricks, even if you don't have the exact value for Q, but just some approximation, some unbiased approximation of this transition quantity. So there is a way to estimate in a very general format to estimate this kind of model using the general Poisson estimator and the trick proposed by Olson and Westerborn. So it's very nice, but it's completely unuseful in the context of movement ecology because it's very computationally intensive and you can only handle a very few successive position. It tends to be too time consuming when you deal with a regular trajectory of animals. But it's like, from a theoretical point of view, it's very satisfying. So going back to the habitat preference, we still want to represent the fact that we have some dependency in the position, but that we evolve in some environment. And the ecologists are estimating what they called
it's okay.
So the ecologists tend to be interested in what they call resource selection function. It's how if you assume that you have some stationary distribution about the abundance of the animals, and you would like to estimate the link between some habitat and the presence of one species. So it's very similar to the idea that Camille was presenting before. So the classic form of this resource selection function would be to model it as proportional to some exponential of the effect of the covariates. So here the CG is the covariate number J, and at point X, and here beta J is the effect of these covariates. And of course, you have some normalizing constant so that you have a probability distribution. And so that's a classical resource selection function. And when ecologists want to estimate this kind of data, classically they use presence absence data, and they try to using some point process model that they estimate this coefficient. But this kind of presence absence data are quite difficult to get, and the telemetry and the fact that you can put a GPS on an animal make it more easier to have data of position, except that there is some dependence over time by this trajectory data. So we'd like to estimate this kind of stationary distribution using some trajectory data. And so we propose to use the Langevin model, which links the stationary distribution to the movement model. So here, saying that the position of animal at time t follow the gradient of the log of this stationary distribution, you can link the stationary distribution of the individuals and its movements. And by doing so and using the classical form of the resource selection function, it's quite nice because the log of P will make the exponential disappear, because you only take the gradients, you don't have to bother about the normalization constant. So the two aspects which could be like disturbing in your model just disappeared by some magic. And then if you agree to make some assumption, we know which is not correct, but it's a classical one, some other assumption, you just end up with a very simple linear model, and it's completely straightforward to estimate it. So contrary to the previous approach where we have like computationally intensive way of estimating parameter, if we have to the price of some approximation, we have a very simple model to estimate the habitat, the preference habitat from an animal, by following its trajectory. And it's very straightforward. It's very easy to make it work. And so it could be used in as an exploration of the data and to have some idea of how animals interact with their environment. So we have some toy example on the sea lions, and so we are able to represent by following several sea lions and assuming that they all follow the same model, we are able to estimate their habitat preferences, and we have this kind of maps. There is some ongoing collaboration working on seabirds in the Mediterranean Sea with people from the Pelagist Institute in La Rochelle and some people from some data from Rodia data with a colleague at INRAE in Toulouse. So we are trying to see if it's really helpful for ecologists currently. There is also the idea that we had before that the preference of habitat could change depending on the internal state of an individual. Of course, when a roe deer wants to hide from a predator, they tend to have some habitat preference, which is kind of different at the moment they want to be fed. And so we'd like to explore the fact that to have some hidden Markov model with a Langevin model. And if we again agree to make the earlier approximation, it's very straightforward because we have a mixture of a hidden Markov model where the observation with the emission is just a linear model. So everything is straightforward. And there is some master project currently working on this aspect to add some hidden Markov components in the Langevin model. And the other idea we are currently working on is that maybe it's a bit difficult to assume. So it's we have some very unsmooth trajectory when you model the speed, the position by this stochastic differential equation. So maybe it's a better idea to think that the environment not directly change the speed, the position, but the speed. And so again, just by a very simple change of model, you can have some eco-elliptic approach saying that you want to model the speed, the velocity of an animal, and you only observe the position. But if you again choose the mathematical model, which is convenient for you, you have exactly the same property because the stationary distribution from the xt process here will be exactly p here in this in this model. So we will have the exact same property, and again it could be expressed using the Euler approximation as a linear model, and we can reuse everything we have developed before, but we have maybe a more smoother representation of the movement by doing so. Just to finish, the idea we are looking for from future work is that the introduction of individual random effect, because animals might respond to environment in a different way. And the critical point currently is that most of the description environments are not given by quantitative data. And here we are, because we are losing the gradient of the potential, we need to have some gradients here of the covariates. So we need to have some quantitative covariates, which are supposed to be smooth enough. And most of the description of the environment as presented by Camille are just, it's in the forest, or it's this part of the landscape is some fields, and so on. So we have like categorical description on the environment. And so for the moment, we use some tricks saying that we present this, we change this description environment by computing the distance to the closest forest or so on, to switch to some quantitative description environment, but it's not completely satisfying. And so we are looking at some extension using some different approach from Leger and Pigato, which are just saying that at some point you cross a barrier depending on your position, and then you switch for movement. I think it's quite famous in financial application, which has like you look at the trajectory and there is some random movement, and at some point you reach a barrier and then you switch to another model. So that's what they have been developing, and we'd like to include this in a 2D approach. And the very long-term perspective is to address the idea of collective movement, because we have more and more GPS, more and more animals equipped with GPS. So we won't have an equipment of the whole of all the birds, but we can expect that just looking at a good amount of birds, we can trying to explore the interaction between between them by assuming that there is some, I don't know, mean-field approximation for the one you don't observe. And there is also new data coming up that with the GPS, we have a lot of data that there is accelerometry on many of them, but there is also now some sound monitoring. And so you can have information, indirect information on the on what the sound the people is reacting to, which could be very interesting because you can have information on long distance, on what happened to long distance. Because for the moment, we just with the model we are using, you just react on the local environment, and the idea to include some sound monitoring in the data in the modeling approach, you can account for, I don't know, when you hear some distant predator on top of this kind of data. And that's it. Thanks you for your attention. I forgot one slide.
Questions?
Yes, I have a question. So at the beginning of your presentation, you said that you reject the possibility of using a discrete process to analyze this data. But do you think it's possible to use a discrete process if, for instance, you put your data in some equally spaced grid? Okay, for instance, taking the high frequency average, and then treat, and then you don't have any more the problem of inequally spaced, but if you have a problem of missing data, that you can solve with the technique in this process, such that you don't need to take the error approximation to estimate the model.
So most people do that. Actually, they even do something more dirty than what you propose, because they just equally spaced data by doing some interpolation. So they are adding some noise by doing so, and then they use it as a equally spaced data. But your suggestion is a good one, to treat it as a missing data, except that you just, the situation is not that you just have one missing point. You can have very irregular, and so you can have several points in a row, especially with marine species. When they dive, they can dive for a while and they completely lose the GPS tracking. So it could be even if you have one position every minute, and then during 20 minutes, you don't have anything.
Okay.
So I'm not sure in this case that this approach would be useful.
So the problem should be that you have just a lot of missing points.
Yeah, and even if it's set up as a regular time step, they can have like some a change in the time step depending on how GPS are present or not.
Okay, thanks.
Yes.
So did I get it right in the first potential that you presented? That was just a mixture of Gaussians.
Yeah.
So that would mean that that does not generalize the Orschen-Uhlenbeck process, right?
It could be like, yes, it could be a mixture of Orschen-Uhlenbeck, for example. It could be kind of thing.
So I mean, this one here with the gradient of the logarithm, this one does give you a Orschen-Uhlenbeck process.
Yes, if you have some Gaussian simple Gaussian process here, you will have the Gaussian process, the Orschen-Uhlenbeck here.
But the other one?
No, the other one is different because it was at the beginning. We didn't know anything about the Langevin approach, and so we didn't link. We just choose this form to have some flexible representation of the potential. But here we are not, so there is no log here, because we are not seeking as a stationary distribution. And actually this kind of data, if you don't have like a closed area, you don't even have any stationary distribution. So it was like the beginning of our work on this subject, and there is this comment is correct. There is no stationary distribution in this situation. Yes.
very interesting talk.
Thank you.
Actually, yeah, to me, it's the same, except maybe you need some interoperability condition on exponential line stage for this to be a non-trivial function. It's exactly the same.
Yeah, that's true. But except that this one has no doesn't realize the assumption.
Because phi is the density of regression.
Yes, yes. And so the exponential, there is no. It's not
With
bounded.
another change of function.
Yes, yes, for sure. Yeah, that's the same idea. And just the idea of the what I call the Langevin approach, but it's just like for me, it's just like it's a very natural way to link with what ecologists are doing currently about the resource selection function. And it was like when we realize that it's exactly like it's meant to be put together because you have this simplification, straightforward simplification.
My question here would be if you specify a target distribution, a stationary distribution, you're looking for movements that leave this environment. You have the whole zoo of instance methods.
Yeah, that's true. Yeah.
And in particular, there are some methods that are very different from Langevin, do not assume any smoothness on the targets. And for example, have trajectories that can be more similar to actual animal trajectories. For example, with periods where the trajectories
it's stuck in yeah.
Periods where it's deterministic. For example, this way is deterministic.
I completely agree. We can all the methods which are used to the Monte Carlo exploration of some target distribution can be used to explore if it's more relevant for the animal movement. And actually, that was the idea. I don't present that, but the idea of the Langevin approach was given by Theo Michaud at the beginning because he was using some discrete representation, but he was like just using some classical MC approach to do that. And he was like, and that's what gave us the idea of doing that. But we can explore all the model, and especially the one which are just switching from one point to the one, and even the Hamiltonian, everything.
And in particular, I guess, because initially you talked about the change points. So when you do MCMC, you can choose to randomize the different methods within one, which I think would be exactly the same. So if you imagine that in MCMC, every time you do a step, you choose at random between multiple steps.
Yes.
Yes,
if you have a mixture for the yes, could be.
You can even
Except that I would like to add some. If I switch to a state, I want to stay in a state for a while. So I don't want to choose the term of the mixture I choose at every step should be different, and everything should be in a continuous time and not a step. So that's something I have to explore. But yes, I agree that all this, as we say, all the zoo of the MCMC method has to be explored. Yes, sorry.
Go ahead. I don't know about this area, but I have general questions. You modeled in R2, right?
Sorry?
You modeled in R2, so on a plane.
Yes.
Why are you not interested in modeling in R3? So when you have also
elevation, and so we can in most of the data I have been working in, I have only GPS data, so it's only a 2-dimensional data. But for birds, I also have the elevation, so I could consider that. And there is some beginning of a project working on, I don't know, I would say mountain sheep. It's not exactly this kind of, but mountain sheep or this kind of stuff. Je sais pas moi, un chamois. Comment on dit un chamois en anglais? So some kind of sheep living in the mountain, and elevation sheep.
yes.
Sorry, goats. Yes, mountain goats.
Yes,
Okay, and for this kind of animal, the elevation is very important because it provides a lot of information on how the shape.
The reason why I asked, I could imagine that fish, because of the warmer weather or something like that, could tend to live at another level. I have many questions, but I don't want to keep you away.
We can maybe discuss after.
Yes, maybe we will have a quick break soon. I don't know. Maybe we can discuss it after, but maybe Pablo had a question. A short one.
Short one.
Ouais.
I'm an anthropologist.
Okay.
So,
Nice to meet you.
coming out of the process. So I was wondering if this is possible or makes sense at all to modify your line diffusion and add a different time scale of the noise, something like add a Poisson compound process. So you have a Levy type noise because there's a, I don't know for your animal, but for other animals there has been this kind of description that they do this Levy flights because they maximize the way they can find things in the landscape.
So it has been done a lot, working on the step lengths and all this stuff, using some Levy flight to explain that you have very long distance between two. So at some point, the animal gets a bit crazy and go very far away from so they use a Levy flight and so the Levy process to do so. I don't know, so the model I'm using, I have no idea if it could be adapt to do so, but from a very naive perspective, for me, this one is just a trick to present a very different movement in the trajectory. But of course, the animal is not, there is no jump in the movement of the animal because it can't disappear at some place and reappear at another one. So it's not really realistic from an animal point of view, but maybe it's a good way to present some very extreme displacement at some rare points. So it could be used for that, but I have no idea if it's doable with this approach.
Thanks.
Thank you.
So maybe we just stop recording for a while, but I wanted, okay, I just stopped the record, but I keep the connection open. Wait, where is that? Sorry, yes. So now this is the talk by Guillaume. Thank you, Guillaume. Sorry. Hello. Hello. Okay, so thank you, Guillaume, for coming from Rosaire, which makes a lot of difference.
Yes, not that much. Thank you, Paul. Thank you, everyone, to be here. So my name is Guillaume Franchi. I am a PhD student at NSAI in Rennes since last October, actually. And today I'm going to present you my work about the modeling of abundance time series in ecology. So I will begin with some reminders about the abundance and compositional data. Then I will present the model we try to build for abundance time series, which is based on a GLM framework and possesses some nice statistical properties, especially when it comes to estimation. And finally, we will try to apply those estimation results on both simulated data and real data set. So there are two main ways to define the abundance in ecology. The first one is to consider the standard abundance, where you simply count the number of species, of individuals, sorry, of each species in the ecosystem. So here you describe the commonness or the rarity of a species in your ecosystem. But there is also an attractive notion, which is the relative abundance, where you consider the proportions of each species in the whole ecosystem. So with relative abundance, you have a vector of proportions with the proportions that must sum up to 1. Here you describe the biodiversity of the ecosystem. Imagine that you have a vector of abundance with 1, 1, and only zeros. It means that you have only one species in the ecosystem, so you don't have biodiversity at all, for example. So mathematically speaking, relative abundance Y, so here you have D species with the D proportions. It is an element of the simplex, which I will denote S D-1. So it is a set of vectors with positive components and the sum of the components, which is equal to 1. There are two notations that will be useful in the talk later. First of all, I will denote the Shannon entropy of a vector of abundance y, IS of y. So it is a positive quantity. Yeah, and in ecology, it is a measure of biodiversity in your ecosystem. The higher this index is, the more biodiversity you have in your ecosystem. And last useful notation, I will denote y with the bar, the vector where I remove the last component of abundance. Actually, here I will consider that the last species is a species of reference in my ecosystem. It is the one that completes the rest. Okay, you will see why later. It is just a useful notation. Okay, so if you want to study a time series of relative abundance, denoted YT here, with these species, there are difficulties that come from the positivity constraint. Okay, every component must be positive, and the sum constraint. So you cannot apply any kind of time series model with this kind of data set. Okay, for example, if you take a Varma model, you may have some fitted values that are negative, and it has absolutely no sense to have a relative abundance which is negative. You cannot have a negative proportion for your species in the ecosystem. So in order to deal with this problem, there is a well-known approach which was proposed by Etienne in 1982. It is very simple. The idea is to transform your time series with an application F that comes from the simplex into another vector space Rn, and you obtain a new time series Zt. So that is equal to F of Yt. And now, because you don't have any constraint on Zt anymore, you can apply your favorite time series model to your process Zt. And eventually, if you want to have fitted values on in the original state space, you can transform back your fitted values Zt hat with the inverse application F minus 1. So in practice, a very popular choice for function F is the additive log ratio that comes from the simplex and goes into R minus 1, and you just take the logarithm of the proportions ratio y1 divided by yd. You can see that the species D is indeed a species of reference here. Okay, this method has shown very, very good results in terms of predictions of fitted values. But there is a big problem when it comes to interpretation, because you apply the model on the transformed time series. And if you want to have an interpretation in the original state space, it is very difficult, if not impossible, to know what the parameters mean into the real world. So our goal here is to propose a model which could be easily interpretable for ecology scientists. So we will work only with the original time series YT. To do so, we propose to define a time series YT by the means of a transition kernel denoted P. Here and in the rest of the talk, I will assume that conditionally to the abundance at time t, the distribution of the abundance at time t plus 1 is defined by this kernel P. So in other words, we will build our time series such that the dynamic of time series is not defined by some kind of autoregressive relation, but it is defined by the kernel P. Obviously, it is possible to consider more than one like values. And actually, you can even take an infinity of path values in your transition kernel. All the results presented here work very well.
So you have to accept.
Oh, yes, thank you. I didn't see it at first. I think it's... Okay, so that is the main idea, but it is okay? Yes. And it doesn't work anymore? I'm sorry. Yes, good. So we have to know how we can choose the kernel P. And we propose that it will follow a direct line distribution. Why is that? Well, because actually the direct line distribution can approach quite easily any kind of distribution on the simplex. It is the generalization of a beta distribution on the interval 0,1, if you are more familiar with it. So it is not a perfect choice, but it is a first try in our work. Some reminders about the direct distribution. I will not enter into the details because I won't have time. But just keep in mind, if you are not familiar with it, that it can be characterized by its mean vector lambda. Okay, so we have the mean of each relative abundance, and the dispersion parameter phi, which must be okay. This is just a notation. Actually, if you have a random variable big Y that follows the direct distribution with mean lambda and dispersion parameter phi, the variance of each marginal is given here by this formula, and you can see that the higher phi is, the less variability you will have. So we propose that the kernel P is a direct distribution with both mean and dispersion depending on fixed parameters eta and theta, and also obviously on the abundance at time t. And following a GLM framework, we will assume that the mean lambda and the dispersion phi satisfy equations 1 and 2. So just a little explanation about these equations. Here, actually, I suppose that the mean lambda, the additive log ratio of the lambda, of the mean lambda, is a linear function of yt bar. And here, remember that in yt bar, I just remove the last component. Why? Because if I choose yt instead of yt bar, I would have an identifiability problem, because you could choose different matrices A or B and obtain the same result. So you would have an identifiability problem, which comes actually from the sum constraint. And in equation 2, well, it is just a way to link the biodiversity, which is here given by the Shannon index, and the variability of the process.
Sorry, what is the ALR?
It is sorry, it is the additive log ratio. If you remember, it is oh,
It's okay, it's okay.
this is this function, yeah, actually. Okay, I could choose another kind of link functions, but I decided to use this one. It works quite well. Yeah. And sorry, I did not mention it, but ALR, it's additive log ratio. So we know how to how do we want to make our process, but we have to be sure that this kind of process exists. If not, it's not worth. It doesn't worth to study it. So this is the point of theorem 1 here. If we make two quite reasonable assumptions, which are only capacity assumptions, we will assume that both theta and eta belong to compact sets. We can prove that there exists a unique time series yt, which satisfies our dynamic mentioned previously. And this time series is strictly stationary and ergodic. So it's okay, we know that this kind of time series exists. Actually, if you are familiar with some Markov chain works, the assumptions A1 and A2 here ensure us that the kernel P satisfies the Dublin's condition. And it is if you are familiar with Markov chain, it is a well-known condition to prove that Markov chain is ergodic. So I promised you that the model could be interpretable. Let's just take a look at these parameters and their interpretation. So if I take, for example, the parameter theta, remember that the dispersion parameter here, phi, is given by this formula. And the channel index is a measure of biodiversity. So if theta2 is positive, it means that the higher the channel index will be, the higher phi will be. And so the lower the variability will be. So if theta2 is positive, it means that the more diversity, the more biodiversity I have at time t, the more stable the ecosystem will be at the further step. It is the exact opposite interpretation if theta2 is positive, is negative. If theta2 is negative, it means that if I have a lot of biodiversity, my ecosystem is actually very unstable. In practice, I assume that theta2 is almost always positive, I think. I won't. I will pass on theta1, just a variability inherent to the process. It's not very, very important. I will focus on the interpretation of parameter eta instead, because it is more tricky, it's more difficult to interpret it, but still, it gives good insight. So I must take a look at the mean lambda, which is given by the inverse of the additive log ratio here. And it is also given by this formula. Okay, so it's quite long and ugly. But if I just consider the first component of vector B, let's say B1, you can see that if B1 is very high, the mean of the first species will also be very high. So B1 is just gives information about the trend or the evolution of the first species. And it is the same for each, for B2, B3, etc., etc. So the coefficients in vector B are interpreted as an inherent dynamic of the abundance of each species. If we want to interpret A, I will consider the expected means ratio. So what I mean here is MR between species I and J and the initial abundance YT is actually just lambda I with parameter eta and initial abundance YT divided by the mean, the expected mean of species J. And it is given by this exponential. If you just compute it, there are 2 lines to do, and you obtain this formula. I star is just the ith line of matrix A. Imagine now, with this means ratio, that I modify my abundance at time t, and I apply some perturbation on this abundance, and I increase the species of reference with a proportion p at the expense of species I and J. The other species, I don't touch them, but only species I and J are affected by this implementation. Alpha is just an impact factor. For example, if alpha is equal to 1, species I is not affected at all, only species J. If alpha is equal to 0.5, it means that both species are affected the same way. So I need some minutes. You can do it. every time it doesn't work anymore. Yes, but if I want to skip the slide. Okay. So I have a new abundance ZT which is modified. And if I want to see what is the impact on the expected mean ratio, I don't have to write it because it's written here. So ZT is the modified abundance, and here it was the initial abundance. It is given by this very long formula in the exponential, and it depends only on the parameters of A, on P and alpha, obviously, but it does not depend anymore on the initial abundance weighting. What is important here is that if this ratio here is equal to 1, it means that our perturbation did not modify the balance between species I and species J. Okay, I could do nothing, and it would be the same if we take a look at the balance between the two species. However, if this ratio is greater than 1, well, it would mean that our perturbation was beneficial to species I compared to species J. And it would mean that the species of reference and species J are more in competition than species I and the species of reference, which was the species D. So actually, it's more tricky, but the coefficients in matrix A give us useful information about how the changes in our abundance could affect the balance between the two species. So we know the interpretation of our parameters. We obviously want to estimate them in a real life scenario. So we assume that we obtain a sample of the abundance a long time, denoted YT. And obviously, we assume that this sample is a realization from the ergodic process we mentioned in theorem 1. So in all the computations, I consider the vectorized form of parameters theta and eta because I had some vectors, some matrices, etc. So I just put everything under a vectorized form. And the most natural way to estimate the parameter is to use the maximum of conditional likelihood. So I won't enter too much into the details. I don't think it's really important here. But obviously, it is here's the optimizer of this function, where P, small p is the best density of the kernel big P. I just give it here. It is the density of a Dirichlet distribution, where alpha I actually is only not writing. Alpha I is just simply p times lambda. It was too long to write. So we can compute this maximum, optimizer, and it has a good asymptotical result because under assumptions A1 and A2, it is strongly consistent and asymptotically normal. So this is a nice property. However, it is very difficult to compute in practice. It's strongly, the optimization of this function actually strongly depends on the initial values you would choose for theta and beta. And in many cases it could fail. Meaning that either it gives us poor result, or a lot of times it doesn't give us any result at all. Because the algorithm, the optimization cannot work. So it is very difficult to compute in practice. That is why we propose another estimator, which we will call the maximum of conditional pseudo likelihood. Here we just modify the function to optimize, and we only consider the parameter eta, which is linked to the mean of the species. Here we have this function to optimize. So we denote our estimator W hat. And what is nice with this estimator is that we only have a convex function to optimize. So we already know that it will numerically it will be easy to compute, and it will work very well. We have the same result. We have the same asymptotic result. So it is also a strongly consistent estimator and asymptotic normal. It is easy to compute, like I said. And actually, a good strategy, if you want to estimate theta, it could be to run previously this estimator W hat and to choose as initial value for eta the estimates obtained with W hat. And in practice, it works quite well, or at least the computer gives us some result. Maybe it's not very good, but in every scenario, it gave me results. Okay, so let's see how this both estimator behave with simulated data first. Okay, so I simulated a 1,000 time series of length 1,002 with 3 species and with these parameters for matrix A, vector B, and vector theta. The numbers I chose were actually some numbers close to estimates in real life, because I wanted to have some realistic abundance. Here is just a graphic of one trajectory a long time. So as you can see, there is a lot of variability here. Okay, the species in blue, which is the first species in blue, it oscillates a lot. And if I take the maximum conditional pseudo likelihood, I obtain this estimates. So this is the mean of the estimates of the 1,000 simulations. And as you can see, it's very close to the true value. Okay, it was 4.5, 3, 5, 6.5. It's very close, and for bits it is the same. If I use the maximum conditional likelihood, so this estimator is not convex, we have some good results for matrix A and vector B, but as you can see, it's a poor estimator for theta. When you want to look at the dispersion, it's very difficult because in real life I have 2 and 0.5. So we are not even close to the true value. So this is a problem. We know that our estimators have asymptotic properties, but how many observations are necessary to obtain a good estimation? That was a question I asked myself. So I just plotted the mean square error of both estimators. In blue, it is a conditional likelihood, so it's not convex. And in red, it is a convex one. So it is better in red, obviously, but I have 2 parameters less to estimate. And actually, you might not see it, but here you have 500 observations. So we really need a lot of observations to have good estimates. And as you can guess, in ecology, it will be difficult because we cannot observe a population for 500 people, obviously. So this is a problem. We will try to address in the 2 other years of the PhD. If we want just to see what it gives on a real data set, okay, so I took a population of birds during 38 years, from 1964 to 2001, and just focus on these 3 species. So I'm not really a scientific for birds, but I just see that they do not look alike, not really, and so I think that there is no classification error when the scientists observe them. Just to see how the trajectory of abundance look alike. So here you have the first species, in red the second one, and in green the third one. There is also a lot of variability, especially in the 90s. As you can see, the species in the red oscillates a lot. it will be a problem later for confidence intervals. You see that. So I use my estimator of I use the maximum conditional likelihood to obtain all the parameters here. So I have some estimates that are quite close to the ones I used in the simulated data, but actually it was the inverse. Before I applied my estimator on this data set, and then I chose for the simulation parameters that are close to this one. And what I wanted to do was to make previsions on the last 8 years, because here I just took the 31st observations to make the estimation. So it will not, I assume it's not very good because I have too few observations, but still, I wanted to take a look at the last 8 years. And the predictions are made step by step, meaning that if I have the prediction at time t, I will make the prediction at time t plus 1 by taking the expected mean with parameter eta hat and the prevision right here. It gave me this result, so it's small. I'm sorry for people that are in the back. So in full line, you have the real trajectory. And in dotted line, I don't see if you see very well, you have the prevision. So here it is, in blue it is here. In red it is here. And in green it is here. It decreases slowly, but then it stabilizes. So obviously there is a lot of variability and oscillations between our previsions, but still it captures quite well the trend of each species during the last 8 years. The ribbons you can see, blue, red, and green, are actually confidence intervals of order 95%. So you will say that, yes, indeed, they are very large and maybe not very useful for estimation because they are too large, actually. But as you can see, and like I said before, there is a lot of variability actually in my time series. And with the red one, you can see that the real trajectory is really well in this confidence interval. We'll skip the interpretation of parameters B and theta. I will just focus on interpretation of matrix A. And I make the same thing as before. I increase the species, the third species, which is the species of reference here, at the expense of species 1 and 2. And I compute the impact on the expected mean ratio between species 1 and 2. It is given by this exponential here, depending on alpha and p. And I just plotted for different values of p, these functions depending on alpha. So obviously, if alpha is equal to 0, it means that only the second species is impacted, is affected by your perturbation. And here the impact is greater than 2, for example. It is normal. Species 1 was not affected at all, so the balance is at the advantage of species 1. But I think what is important is when alpha is equal to 1/2. Because if alpha is equal to 1/2, it means it is a situation where you just had some individuals of the last species. So you increase the last species, but you don't really touch the other ones. You don't hunt them, you don't decrease them. You just add some individuals of the last species. And here, the impact is 1, it is here. So it is greater than 1. So it means that the species 2 and species 3 are more in competition than species 1 and species 2. If the estimates are correct, it will mean that actually, if we add some birds of the third population, it will be negative for the second one compared to the first one. So the balance will be good for the first species here if we just add some individuals of the last species. Okay, so in conclusion, what I presented here was the construction of an ergodic time series with a good interpretation of the parameters. and good estimation results. But like I said, in ecology, we won't have many observations to do our estimations. So maybe it is possible to construct the same kind of model, but another estimator with the use of panel data. Maybe if we have a short period of observation, but with multiple sites, we will be able to build a good estimator, and it will be feasible. Another problem that I did not mention previously is the problem of zero values in our data set. Because the directed distribution actually only allow positive values, and we cannot have zero values with the directed distribution. So it will be can be a problem with the real data set. You can have, I would say, true zero values, where at some time t the species is not present in the ecosystem. But you can also have false zero values, meaning that the species is present, it is here, but it is not observed by the scientist. So if you have false zero values, maybe you can infer the missing values in different ways. But how does it affect the estimation? I don't know. So this is maybe an idea, but how can we do that? But if you have zero values, true zero values, maybe it's possible to build another kind of model, always on the simplex, but with the dimension of the simplex, which can vary a long time. For example, if the species is not present, you still use a model on the simplex, but the dimension can vary a long time, can be reduced or augmented. Thank you very much for your attention. If you have some questions, I will try to answer it the best I can. And just put here the references I use in the slide. Okay.
Other questions or comments?
Yes.
So, I mean, you described these dynamics for the relative abundance. You know if there could be some sort of dynamics on the absolute abundance that give you this as a
yes, I think I don't have it here, but there was an article with the standard abundance, and it was I think it was also some kind of Poisson distribution that were used.
I think that would yield your model as.
It's not exactly the same. It's not the same, and I think it doesn't. I don't remember, but I think they don't have good estimation results, because here what is very important is the capacity of the simplex, because everything is bounded and everything works well. But if you take standard abundance, it is not bounded, and maybe it's more difficult. So, but I think that there exists some ideas or some bits, some works about that. I don't remember which article it was. I have it somewhere.
Do you think that would be an interesting question?
Because I think, but actually, I just began that last year, and I don't have enough. I don't know how you say that in English, but I'm in my work and I don't see everything that is possible. So I think, my point of view, it would be interesting, but I don't know. Maybe some more experienced ecologists would answer differently. But I think it should be interesting to adapt this kind of model to standard abundance with real counts of species. Yes?
Yeah, I'm not sure if I got some for that. Is your model Markovian at the
It's not necessarily a Markovian. It really looks like a Markov chain, but actually we do not have. It's not mandatory to have the independence with the past. So I think it's not entirely Markovian, but it is really close to. I really see what you mean, because actually all the proofs of the results are not exactly the same, but really close to the proofs in the case of Markov chains. You just have sometimes to adapt one or two things. So I would say it's not Markovian, but it's really close. Here, because if I wanted to have something which is really Markovian, I would say that that here you should have another condition of independence with all the past. Here I just know the conditional law between these two steps.
Okay, so in all the estimations you have put out there, you have used pairs of observations.
Yes.
And so on, so that's enough to describe finally the estimated things without describing the law of the whole vectors of the observation.
Well, you just need effectively, you just have to know the dynamic between two steps and describe the law of the entire process defined on the integrals. It is really necessary. This is the only thing necessary to build the entire process. It's a really long proof, really long. I found it hard for me. And that is kind of yes, kind of magical because I would say that knowing only the transition between two steps, you could implement all of them. You start from 0, and then from both sides in the set of integers, you meet all the marginal laws of the process, and at the limit, you get the process of you get the distribution of the whole process. But you just need 2 steps. Yes.
Can you comment on you mentioned in one of your slides that the volatility increases with the number of species. And I'm asking you this because it has been observed that the contrary might also happen. We call it the portfolio effect. So the more species you have, the damp the fluctuations because they average the fluctuations. So, but this is interesting that you observe the difference.
This was maybe more on this remark, maybe.
Yeah, at some point you mentioned it, but you didn't actually talk about it, but you just posted in your slide that the volatility.
Yes.
Right.
Well, yes, in here in this model, it depends. The volatility is well described with this parameter, I think. Because I don't know if how it works in real life. I would say that yes, if there is a lot of biodiversity, I would imagine that the ecosystem is more stable, more balanced.
Okay.
But in the model, it could be the inverse if you have a negative value for θ2. So in our estimates in real life, we had a value of θ2 which was positive. So we would say it would mean that the more biodiversity we have, the more stable is the ecosystem. But maybe in some situations it's not the case. I really don't know. But I think this model could give us good insights, indeed, on some ecosystem. How do they work?
I'm sorry. May I suggest that we go on discussing during the lunch?
Yes.
I have to apologize. I didn't prepare well to your talk, so I just have shishis on my shirt. I will try to correct it soon.
Thank you again for your attention.